Welcome back to Meaning from Data, Statistics Made Clear. Today we're going to talk about one of the most common statistical statements that we read in the newspapers, which is the headline that we see every election, which will say something like this: Candidate A will receive 59% of the vote with a margin of error of plus or minus 3%. So in this lecture, we'll see what a statement like that actually means, and also why that statement is just simply incomplete as it's written. It simply does not contain a meaning if it didn't have some other presumption that is not stated in that statement. So let's the format of the lecture will be to just look at some examples that will make this hopefully clear, and we'll begin with the concept of an election where we have two candidates, imaginatively named A and B. So we are thinking about trying to find out how the population of all the voters in the country are likely to vote, and our strategy is quite simple. What we do is we just take 1,000 people at random, always at random of course, and we ask each one how he or she will vote in the upcoming election. And one of the points of this lecture is going to be to answer the question, how many people do we need to ask to be how confident? Remember that in some sense, the goal of statistical analysis can be summarized as how close and how confident. And we're going, in this lecture on confidence intervals, we're going to answer those questions. How close is our guess going to be? That is what the margin of error is going to be. And how confident are we that, in fact, we are close enough? Now, in our example here, talking about statistical polling before an election, we're going to make the following assumptions, none of which, incidentally, is actually true in the real world, which is a big issue that we'll talk about later. But first of all, let's assume that everybody tells the truth. Second, let's assume that every person that we ask actually answers the question. You can see that none of these is actually true. But third is that all the people that we ask are in fact chosen completely randomly from the general population. They're always all voters. They actually will vote. But these are issues that are very problematic in practice. And so what this lecture really is about is the mathematics of how we do confidence intervals, which is what's actually reported. But there are other issues that we have to realize that in reality make the answers to how accurately we can assess future voting trends that make it all the more difficult to actually ascertain. Well, the goal, as is often the case when we're taking a sample from a large population, is that what we really want to know is how the voting population at large, all the voters in the country, are going to vote. Maybe there are 100 million voters. We, once again, don't really care about the specific, say, 1,000 people whom we're asking. I mean, there's nothing special about them except as they are trying to give us evidence for how we are going to make a guess about how the 100 million people are going to vote. So this lecture completes the promise, really, from Lecture 3, the Introduction to Statistical Inference, where we first described the concept of gathering from a sample of a population an answer about the whole population. We're answering the question, how close and how confident? We're going to quantify those ideas. So let's begin with our example. And as I said, we'll assume that we have an election coming up, and we're going to ask a certain number of people how they will vote and try to ascertain what we're going to declare as that headline in the paper of how close we are to guessing the total voting population and how confident we are that that is correct. So let's begin with an example of a poll that would not actually be undertaken in real life because it's too small. So suppose that we have a poll of only 10 people. You randomly choose 10 people, and suppose that the actual answer is that 60% of people are for candidate A. then what would we expect when we take a poll of 10 people as how often would we expect 6 of those 10 to say that they're for candidate A? How often would we expect 7 of them to say they're for candidate A? 5 of them, 4, 6, 9, 10. We could get any number between 0 and 10 for candidate A. We're only picking 10 people. But it's more likely that we will get 6 people for candidate A. It's somewhat less likely that we get 5. And here you see the dots are an accurate representation of what proportion of samples of size 10 have 0 people for candidate A, 1 person for candidate A, 2 people for candidate A, 3, 4, 5, 6, 7, 8, 9, and 10. So if you choose just 10 people and ask them, you can see that it is rather likely that you'll get between 4 and 8 people for candidate A if the reality is that in the population 60% are for candidate A. But look what happens if we take a larger number of people. Then the proportion of our samples of size, in this case, this diagram has to do with samples of size 100, a much higher percentage of samples of size 100 are closer to the 60% reality of the voting population. Likewise, if we go on and take a sample of size 1,000, then the proportion of groups of size 1,000 whose fraction of people for candidate A, they tend to get closer to the reality of the whole population. So this is a basic principle, and by the way, I have to confess to you, if this sort of seems like deja vu, it's true. We've done this before, and in fact, the whole purpose, in a way, of our previous lectures on probability and were to illustrate this idea that as you take larger samples, those larger samples are having a higher fraction of the samples that are closer to the actual population mean. So here we go, and you can see in this diagram we have all of these represented. That is, this low line here shows us that samples of size 10 are more apt to include samples that differ from the actual correct answer of 6 out of 10 compared to the green ones, which were samples of size 100, and then this tall one, which is samples of size 1,000. As we get more people, we're more apt to get a good representation of the world. However, we want to point out that we may not get the good representation of the world. It's certainly possible to ask 100 people at random, and all of them are for candidate A, or all of them are for candidate B, even though 60% of the people in the world are for candidate A. So let's assume that after taking our poll, and now let's assume that we don't know the answer. We don't know that 60% of the population is for candidate A, because in reality, when we're taking a poll, we don't know that. So suppose that we do our poll, we ask 1,000 people, and 59% of them, that is 590 of those people whom we asked, say, I will vote for candidate A. So the question that we're going to answer in this lecture is, what can we conclude from that? And so here is what we conclude. We say, okay, in the actual world, there is some percentage of the people who are for candidate A. Maybe only 30% of people are for candidate A. If only 30% of the people were for candidate A, what's the chance that I would have gotten a sample where 59% are for candidate A, where 590 out of 1,000 are for candidate A, if on average in the whole population only 30% are for candidate A? The answer is it's a very remote chance. Very remote chance. And so the hypothetical work that we're doing is to say, if the actual reality in the world were that 65% were for candidate A, what's the chance that I only got 59% for candidate A in my sample? If the reality were only 55% for candidate A, what's the chance that I got 59%? So what we'll do is just look at the following diagrams. This first diagram describes a hypothetical situation where we assume that in reality, 53% of the population is for candidate A. The graph shows us what proportion of samples of size 1,000 have various percentages for candidate A. We can see that if 53% of all voters are for candidate A, then most samples of size 1,000 have somewhere between about 500 people, that's 50%, and about 560 or 56% for candidate A. Remember the last lecture about hypothesis testing? Well, let's do a hypothesis test here. Let's consider the null hypothesis that the world really contains 53% for candidate A. Now, we took a sample of 1,000 and found that 590 or 59% of that sample were for candidate A. In doing this hypothesis testing, remember that the strategy was to hypothesize something about the world and then see whether the evidence we find would be rare under that hypothesis. In this case, where we hypothesize that 53% of all voters are for candidate A, then we can look at this graph to see whether getting 59% would be an unusual event. And we can see that 59% lies way out on that thin part of the graph. Specifically, we would reject the null hypothesis that 53% of voters are for candidate A when we found that our random sample had 59% for candidate A because less than 5% of samples of size 1,000 are that far or further away from the hypothesized value of 53%. And in the language of hypothesis testing, we would reject the null hypothesis that 53% of the population is for candidate A at a significance level of 5%. Okay, so 53% should be rejected. How about 54%? We entertain the hypothesis that the true proportion of the population for A is 54%, but we also reject that hypothesis because our sample proportion of 59% is still too far away. 55%? We reject that also. But look what happens when we consider 56%, the red curve. At about 56%, it's actually 55.9%, by the way, we find that our sample of 59% would not be sufficiently far from 56%, that is, sufficiently unlikely to occur by chance, for us to reject the null hypothesis that the true population proportion for candidate A is 56%. So that boundary value, that break point where the percentage hypothesized is close enough to our sample percentage that we would not reject it as a null hypothesis, is the lower end of the confidence interval that we are creating. In this case, that value is 55.9%. Now look, let's now move on. We'll consider 57%, 58%, 59%, 60%, 61% as hypothetical values for the true population proportion. For those values, getting a random sample of 59% is right among the most expected values for most samples of size 1,000. So we would definitely not reject any of those values in a hypothesis test. So all those values are in the confidence interval. We continue considering hypothetical worlds until we reach the first value, that's this blue curve, and in this case it's about 62%, actually 62.1%, where the sample that we found of 59% for candidate A would cause us to reject the null hypothesis that the true population proportion is, in this case, 62.1% for candidate A. Okay, let's just review the whole situation. We took a sample of 1,000 voters and found that 59% of them are for candidate A. Our feeling is that it's likely that the actual proportion of the population that is for candidate A is 59%, or not too far from 59%. The proportion of the population for A probably lies somewhere in an interval centered around 59%. We came up with the interval from a little under 56% to a little over 62%. That interval is called the 95% confidence interval because there's a 95% chance that the true population proportion will be somewhere in that interval. Or stated another way, when we got a random sample of size 1,000 in which 590 people, or that's 59%, were for candidate A, then the interval 59% plus or minus 3.1% is the set of all percentages that we would not reject as a null hypothesis in doing a hypothesis test at the 5% level of significance. So, when we take a sample, we can produce a confidence interval that we expect to contain the actual population proportion 95% of the time. So we did some simulations here on a computer that did exactly this same kind of experiment. That is to say, we took from a population where the actual population mean was 60%, we took groups of 1,000 and saw what the probability, what percentage of those people were for candidate A, and then put a margin of 3% on each side. And then that gave us, or actually a little more than 3%, that gave us this 95% confidence interval. And you can see that what happened here is that all of these black lines, each one of these is an experiment of choosing 1,000 people at random from a population where 60% are for candidate A. And for each of these lines, the ones that are black have the property that their span does in fact include the true population percentage, which is 60% down here. In other words, if I draw this straight line up, you'd see that the straight line does hit each of the black lines. But on three of our simulations, we got intervals that did not include the true population. What that is telling us is that when we read this headline in the newspaper that says that the voting, the people who are for candidate A are 59% plus or minus 3%, well, 5% of the time, by luck alone, that interval will fail to contain the actual population mean. Now, why do I say 95% confident? Notice that this is a word that is not mentioned in the newspaper headline. The newspaper headline said it's 59% plus or minus 3% margin of error. The implication when it is not mentioned how confident you are is that you're 95% confident. And the reason for that is purely historical and purely arbitrary. There is no reason why you couldn't have chosen 4%, 96% confident or 90% confident. So let's think about what this means. Suppose that you wanted to be more confident. You wanted to have an interval that contained the correct proportion of the population at least 99% of the time instead of just 95% of the time. If you took your sample of 1,000 and 590 people were for candidate A, you would have to declare just a much wider plus or minus interval. You see, because if you have a wider interval, you're more apt to contain the true population mean, and therefore you can make yourself 99% confident on that by having those two red and blue graphs spread out so that the 59 is in a much thinner part of those two graphs. You follow me? So that it would happen only 1% of the time by chance alone that you'd get 590 people for candidate A if you were out to say maybe 65%. Okay, so this illustrates the idea that a confidence interval doesn't always capture the population mean, but 95% of the time, on average, it does. And here are some more simulations that, in this case, of all these simulations, only one time did it fail to do it, whereas in this simulation two, this time, on 5 different occasions, the simulation failed to capture the population mean. So this is the basic idea of confidence intervals. Now I'm going to describe how many people you need to take a sample of in order to be how confident. So what we're going to do is go through an example to illustrate how you choose how big a sample you need to take. And we're going to have the goal, the first goal will be, how can we get a confidence interval that is only 3% off on one side or the other? How many people do we really need in reality to take in order to have a 95% chance of being within 3% of the true population mean? So we'll start off with this diagram that illustrates what's happening in reality. We have a certain number of people for candidate A and a certain number of people for candidate B. And in this case, you can see that roughly 60% are for candidate A, but we're just assuming we don't know what that percentage is. But it's somewhere close to maybe a few more for candidate A. So we can draw a histogram, a very simple histogram, where we just put all of the people who are for candidate A at the point 1 and all of the people for candidate B at the point 0. And then if we take the mean of those numbers, we get 0.6. So the mean is telling us the percentage of people for candidate A. The mean is whatever this height is when the two heights add up to 100. You see, the two heights add up to the 100%, and we're putting the number on this side are the ones for candidate A at the 1, and at 0 we're putting the other people. So the computation of the mean, suppose that we have P is the proportion of people, so it's a fraction, like 0.6, if 60% are for candidate A, then the number of these 100 million voters who we put at number 1 are the proportion of people times 100 million. And likewise, we put 100 million times 1 minus P, those are the remaining people, are put at 0 in our histogram. And so computing the mean is just done by taking this 100 million people times P. 100 million times P is the number of people who are sitting at 1. So we multiply that by 1, and then 100 million times this, 0. Of course, that's just 0. The 100 millions cancel, and we just get P. So this is why when you have that little histogram where the bar at 1 it has P percentage of the people and the bar at the other one has the rest, then the mean actually is P. So that illustrates that fact. Now, we have then a distribution. And when we have a distribution, we can find the standard deviation of the distribution by remembering the definition of the standard deviation. Remember that the way you get the standard deviation is you first find the sum of the squared differences from the mean, and then you take the average, the mean of those squared differences from the mean. That's the variance. And then we took the square root of the variance to get the standard deviation. So let's just, we'll go through this in detail. So if you have this number of people, 100 million times P people, which is the number of people in that bar at 1, each of those people is 1 minus P distance from the mean of the population. Because you see, each person over here is at 1, and here's the mean, which is at P. And so the difference between these two is 1 minus P. That's that difference. So we square the difference of the distance between 1 and the population mean, and each person who's at 1 contributes such a contribution to the sum of the square distances. Remember, we're taking each individual in the population, taking its distance to the mean and squaring it and adding them up. And then we'll take the average of those, the mean of those. And so we then look at the people who are at 0. The people at 0, right here, each person who's at 0 is distance p away from the mean. So if we square that distance, p, we get p squared. So the number of people, 100m times 1 minus p, is the number of people, each of whom is p distance from the mean. If we just do a little bit of algebra here, we see that this is the answer. It's 100 million times p times 1 minus p. And the variance, as you recall, is when we take the number of people in the population, which is 100m, the 100m's cancel, and we just end up with p times 1 minus p. So p times 1 minus p is the variance. That is the average squared distance from each person to the mean. The square root of that is the standard deviation, square root of p times 1 minus p. The goal that we're trying to accomplish is to ask how big a sample size n do we need to take for us to have a 95% confidence that we're within 3% of the true population mean, the true portion of the population. Well, we need to remember a couple of things. First of all, in a normal distribution, you may recall that 95% of the material under a normal curve lies within 2 standard deviations of the mean. Remember that from lecture 6. So our real goal is to have a distribution so that is a distribution of our samples, those peak curves that we saw before. We want a distribution of our samples so that 2 times the standard deviation of the sample is less than 3%. And that way we'll know that 95% of the time we're within 3% of the true value. So here we go. If we take n people as a sample, you may remember that we've discussed briefly the central limit theorem. The central limit theorem said that if you have a distribution and you take a sample, you take all samples of size n, a fixed sample of size n, and for each sample of size n you take the mean of those, and you get a value. So you take every sample size n, you take the mean. Take a sample size n, take the mean. That we saw that the central limit theorem states that the standard deviation of the samples of size n are smaller than the standard deviation of the original distribution that you started with in a predictable way. Namely, you divide by the square root of n. It becomes thinner by dividing by the square root of n. So in other words, if we take samples of size, say, 100 from a distribution, and we take every group of 100, we take the mean, and that's a value. Any every group from 100, we take the mean, and that's a value. We get a distribution. The distribution will become bell-shaped. That's also part of the central limit theorem. It becomes bell-shaped, and it's the width of it, the standard deviation of it, is going to be 1/10 of the standard deviation of the original population if we take samples of size 100, because the square root of 100 is 10. See? So here's, in our example here, we know the standard deviation of our original just population that has 2 bars, people at 1, people at 0. Its standard deviation, which we just computed, was the square root of p times 1 minus p. So the standard deviation of if we take samples of size n, the standard deviation is going to be only 1 square root of nth of that. That is, we divide by the square root of n. The square root of p times 1 minus p is never going to be bigger than 1/2. And this is just some arithmetic. Suppose p, remember p is a number between 0 and 1. If p is a half, we have a half times a half. The square root of a half times a half is a half. If we have a number like p is equal to 0.6, then we have 0.6 times 0.4, which is 0.24, which is less than 0.25, and so its square root is smaller than a half. You see, so you never, So this value here is never bigger than a half. So we can just see that this standard deviation of the means of sample size n is never bigger than 1 over 2 times the square root of n. 1/2 times 1 over the square root of n. So you can see that it's getting smaller. Our goal is to make 2 times the standard deviation of our sample less than 3%. So just doing the plugging in for sigma is the standard deviation, and this is an upper bound for the standard deviation. So 2 times that is less than 3%, which is equivalent to just doing some multiplying through. The 2's cancel, square root of n comes over here. Square root of n has to be bigger than 1 over 0.03, and just squaring it to get n. N has to be bigger than or equal to 1,111. So all of this work, and you know, I certainly don't imagine that you necessarily followed every step of that, but all of this work tells us that if we take a sample of size 1,111, then we can be 95% confident that the 3% interval, a plus or minus 3 error, will capture the actual population proportion. So this is, I know this is a little technical, but it gives you at least the flavor of how these things are done. Suppose that you wanted to be much more confident. For example, suppose you wanted to be 99.7% confident that a 3% interval contained the correct answer. Well, then you do exactly the same analysis. You're trying to find out how big the n would have to be. Remember that in a normal distribution, 3 times sigma is the 99.7% level. In other words, in a normal distribution, 99.7% of the material is within 3 standard deviations of the mean. So we're looking at the sample means, samples of size n, and we want 3 standard deviations to be less than 3%, and doing the exact same work we did before, we see that the sample size would have to be bigger than or equal to 2,500. I wanted to point out just one other feature, and then we'll stop. And the feature is that notice that the size of the sample, in order to get confidence that we're getting close to the correct answer, is not determined by the total population. It didn't matter that there were 100 million people total voters or just 1 million people total voters. The numbers that we were getting were just determined by an absolute number. And the analogy for this is the following. Suppose you were creating chicken soup. You know, you're cooking soup. You don't create soup, but you're cooking soup for your family. And you have a little saucepan. And you want to know whether or not it's salty. What do? You stir it up, you take a spoon, you taste it, see, is it salty? If it's perfect, it's perfect. Now suppose the next day you're volunteering at the local soup kitchen. You have a big vat of soup that's going to feed hundreds. What do you do to test how salty it is? You stir it up, you take a spoon out, and you taste it. And you say, is it the right saltiness? If so, fine. You don't have to take the same proportion out of this big vat. You don't have to taste a whole, a big tureen of soup in order to tell whether it's the right saltiness. So that's the analogy to saying that the absolute size of the sample is what tells us the confidence. So in this lecture, we've seen we've gotten to the promise of how to tell how close we are and how confident we can be that we are that close. See you next time.